Cassandra's always punched above its weight on throughput and availability. What the community is focused on now is the other side of that, making it easier to operate, automate, and manage at scale. The Cassandra enhancement proposal process is where the community is actively working to fix these things, and today we're going to walk through 5 accepted CEPs that together touch many aspects of how Cassandra is operated. So let's get into it. CEP 38, the CQL Management API. Right now, most Cassandra admin tasks, like taking a snapshot, running a compaction, anything you do with no tool, route through JMX and Beans. The ecosystem has worked around this over the years by wrapping JMX in REST APIs or by bypassing it entirely with Java agents. But JMX was never designed as a stable contract. It carries security exposure, adds operational complexity, and makes it hard to build reliable automation on top of it. CP38 adds a native CQL interface. Each admin command is defined once in a single registry with structured metadata and exposed consistently across interfaces. So no tool in CQL/SH stop being separate implementations and become thin entry points over the same operations. There's also a shift in the execution model. Instead of submitting a command and blocking until it completes, a command returns an identifier that you can use to track and observe its result asynchronously. This matters a lot if you're building automation or higher level workflows. Importantly, this does not deprecate JMX. Existing tooling keeps working. It moves the project toward a state where deprecation eventually becomes feasible. CP45, mutation tracking. Repair and read repair are Cassandra's current mechanisms for catching missed writes. Both work by pulling stored data from multiple nodes and comparing it. However, that comparison is expensive. Repair ships whole partitions between nodes when it finds a discrepancy. Read repair only fixes the slice of a partition a query actually touched, which can leave a write half applied. CP45 takes a different approach. Instead of comparing data on disk, each write gets a unique ID that travels to its replicas. Each replica records which IDs it has applied. At read time, one replica returns the data plus a summary of its applied IDs, while the others return only the summary. Matching summaries confirm accuracy. Any gaps are filled by sending only the specific missing writes, not entire partitions. In addition, a background process continuously reconciles these IDs across replicas and establishes a lower bound, which is similar to a watermark that signals when older log entries can be safely cleaned up. The practical benefit for operators is lower streaming costs during reconciliation and the prospect of relaxing the need for full anti-entropy repair cycles. Cassandra ships with 4 compressors: LZ4, ZSTD, Deflate, and Snappy. Compression runs during flush, compaction, commit log writes, and data movement across the network. On clusters with heavy compression workloads, that adds up to a meaningful share of CPU. Some modern processors carry built-in accelerators for exactly this kind of work. Intel's Quick Assist technology on Xeon chips, for example, can accelerate LZ4, ZSTD, and Deflate. CP49 adds a framework that hands compression off to that hardware where it exists, freeing CPU for other tasks. The framework is pluggable. Backends ship as separate plugins, but that Cassandra discovers at startup. If a plugin fails, Cassandra falls back to the standard software compressor automatically. The hardware must already be correctly configured, and anything not functioning defaults back to software-based compression. The main beneficiaries are operators running compression-heavy workloads on capable software, but the framework is designed to support other hardware-based compressors in the future as well. CP60, flexible placements. A node's token positions on the ring determine which data it owns. Growing a cluster cheaply tends to require doubling it. While a node joins, its range is temporarily served by an extra replica, which adds load. On vNodes, tokens can't be moved, so fixing an unbalanced ring falls entirely on the operator. CP60 decouples data placement from token position. The unit of ownership becomes the tablet, which is arranged for a specific key space and table pair, with replicas assigned directly. Built on CEP21's transactional cluster metadata, it lets Bootstrap and streaming run in smaller, resumable steps. Placement decisions use per range load and capacity metrics rather than ring percentage. The operational benefit is steadier node utilization. Token-based growth produces a sawtooth pattern that forces operators to provision for the peak and pay for the idle capacity. With flexible placements, the cluster stays close to balance at any size, which translates to higher, steadier utilization and fewer wasted machines. CP62, Cassandra Configuration Management via Sidecar. Many Cassandra settings live in cassandra.yaml and can't be changed while a node is running. Startup tuning, like heap size and garbage collection, lives in JVM option files. For these on-disk files, Cassandra is offered no programmatic interface. Operators edit them by hand or with custom scripts, with no version awareness and no centralized control. CP62 fills that gap with a Sidecar REST API for reading and modifying Cassandra.yaml and JVM option files. It layers a sparse overlay of explicit changes on top of a base template and merges the two into a configuration the node actually uses. A pluggable provider can store overlays locally or in a central system like etcd or console. A version-aware check rejects settings a given Cassandra version wouldn't recognize, reducing the risk that a bad setting leaves a node unable to start. Changes apply on the next restart. The feature is disabled by default and purely additive, so existing deployments are unaffected. To wrap up, we discussed 5 CEPs: a programmable management API, write-level mutation tracking, hardware's accelerated compression, decoupled data placement, and programmatic configuration management. Each one targets a real operational burden. The CEP's inclusion in release depends on a successful implementation, testing, and approval by project committers. These 5 have been accepted, and following the CEP process is one of the best ways to track where Cassandra is headed. If you want the full breakdown with technical details on each proposal, the link to the blog is in the description. And if you're running Cassandra at scale, whether self-hosted or through a managed provider like NetApp Instacluster, these are the proposals worth keeping an eye on.